All right. Hi, everybody. Welcome back to the technology stage. It was a very eventful morning for us here, and we had three wonderful presentations that really talked about some of the issues and some of the progresses we've made as a community in additive manufacturing. This afternoon, we have we'll be focusing on a software part. So we'll be discussing data, digital thread, and pretty much cybersecurity this afternoon. We have a first presenter here, and pretty much we'll introduce her shortly. Our next presenter is Azade Agigi. She's a research assistant professor at the University of Illinois Chicago. This afternoon, she is joining us from Chicago, and we'll be discussing a topic she titled "Leveraging Process Physics for Data Efficient Learning Towards Smart Additive Manufacturing." Welcome, Azadi, and whenever you're ready, please take it away.
Okay, thanks a lot, Adi, for the kind introduction, and thank you all for being here for my talk. So as Adi mentioned, the topic of the talk is leveraging process physics for data efficient learning towards smart additive manufacturing. Now, before I actually go into the talk, I just want to give you a brief introduction about myself and my research group. So I'm with the Faculty of Mechanical Industrial Engineering, University of Illinois, Chicago. I'm the director of the Smarter Lab at the College of Engineering, where we do a lot of research at the interplay of robotics, additive manufacturing, and data analytics and AI, because we believe these are the three of the main pillars for the future manufacturing. And we also do research on new innovative additive manufacturing capabilities. You also see like a couple of my past activities, and I'm so proud to be a part of this growing community and happy to be here. So thanks again, everyone, for being here. So just overview of additive manufacturing. I'm sure all of you are familiar with this technology, and that's over here. So it has created disruptive possibilities, both in terms of like the new products and the new innovation in the materials and etc. So in terms of its evolution, we have seen that recently additive manufacturing has been adopted as functional products in critical industries. So it's getting away or basically getting distance from its first applications as prototypes. And as a result, ensuring that a final product quality or the part quality is good or satisfactory has become much more critical than ever before. However, this is actually the portion that IT manufacturing is kind of lacking. So there has been a lot of research going on to try to address the quality challenges. Now, in many of the additive manufacturing processes that the bonding or the fusion of material is basically thermally induced, we actually face a lot of challenges for the quality, like the voids or pores that are happening, the roughness of the surfaces or deformations and distortions that are caused by the frequent thermal cycles. So how to basically formulate this thermal signature and thermal history has become the key in kind of controlling the quality issues in those type of additive manufacturing techniques like the laser powder bed fusion or even fused filament fabrication process. So from the research point, there are several directions. One of the directions for formulating the thermal signature is using models and physics-based approaches. So generally, either analytical or numerical methods like finite element simulation modeling are used. And in terms of basically advantages, so they're really good to formulate and simulate complex systems. So for example, on the top right, you see a thin wall, a finite element analysis for a thin wall that has been basically simulated. And at the bottom, we have the simulations for a melt pool. And of course, all of these are very insightful. However, physics-based or model-based approaches generally have some limitation with respect to capturing the variations of uncertainties of the project. So they're generally deterministic in nature and cannot really address the variations or uncertainty or stochastic nature of mini manufacturing processes, including additive manufacturing. In terms of computation, they're generally expensive. So majority of the studies we see in the literature are limited, for example, to single track or small sample sizes, thin walls, or simple geometries. And as a result, it's really hard to scale them or generalize them to different geometries or processes. And for real-time decision-making applications, which is generally what we're kind of heading through for additive manufacturing and smart additive manufacturing, they're less practical. Now, the question would be how to increase the versatility of these approaches and basically address the limitations that they have. So another direction of research uses data-driven machine learning-based approaches to formulate thermal signature. And of course, again, these approaches have a lot of different advantages, but have also challenges and limitations on the side. The main challenge they have is that they require massive data sets. And in most cases, these data sets need to also be labeled, which is time consuming. The data acquisition pre-processing also is very costly and time consuming. And there are always a lot of like outliers or noisy data that need to be handled or pre-processed accordingly, which adds to the complexity of the process. We have high dimensional data in most cases, and also multimodal data. So we might get, for example, image data, video data, time series, or scatter measurements. So how to fuse this information together and how to, for example, extract valuable information from these different data sources is becoming challenging. And most importantly, data-driven machine learning-based approaches are really hard to interpret. So in terms of transparency, they're not really useful for manufacturing decision making. In other words, it's really hard to understand why the machine has made such a decision. So that kind of logic, which is generally derived by some physical phenomena, is lacking by these approaches. And that would be really hard for manufacturers and decision makers to kind of interpret the system that way. So the question that the researchers are trying to address is that, can we integrate both physics-based and data-driven approaches? Is there a way to kind of basically leverage the benefits and advantages of both of them? And the answer to that is yes. So I think until year 2020, there have been so many efforts in the literature, especially in the field of additive manufacturing, where people are trying to kind of not fully integrate, but kind of combine data-driven approaches with physics-based approaches. So I call these methodologies hybrid methods. So on the left, you can see them. So hybrid methods, generally, the idea is that there are parts of the decision that data-driven or machine learning-based algorithms that can help with. And then the output of those, for example, neural network or machine learning algorithm could kind of inform my physical model in some way. So the output of one could be the input of the other, or vice versa. And this actually creates step-by-step decision making. So we actually implement each of these methodologies in a sequence, not like really fully integrated. So recently, I think since 2019, 2020, we have seen a surge of interest in publications where people are now trying to go beyond hybrid methods and to figure out ways to really truly integrate physics domain and physical information and domain knowledge into the machine learning and data-driven algorithms. And there are different ways that people do that, and I will talk about it in future slides. But the reason for this surge of interest has been the unique application domain of additive manufacturing. So we know that we're getting away from like mass production and moving to mass customization, and we want to make sure that the decisions are transferable, they can be interpretable, and they can be, for example, generalized to different geometries, different processes, and etc. And we also, for the case of additive manufacturing, we have limited data to train. So we cannot generally train our data on, for example, one specific geometry and use it for another geometry unless, we train our model in a specific way so that it becomes transferable. So there are a lot of challenges with those, and as a result, if we can incorporate the physical models and the data-driven models, really integrate them in like beyond what hybrid methods do, we might be able to actually address these specific challenges. So this is just an example, for example, on how hybrid methods work. So hybrid methods, as I said, they are like performed in a sequence. So this is one of the studies we had in our group. So we tried to use hybrid models to characterize the bonding and void in extrusion-based process. So here on the left, top left, you see some specimens, and you can see that the porosity or the voids, that's a structural void that is caused within this specimen, and also between this specimen, the distribution of that kind of varies both along the x-axis, y-axis, or along the z-axis. So if we can, for example, characterize this distribution well, then we can also have an understanding of how the part will perform like at different local regions in terms of mechanical properties. And of course, like one way is to use theoretical models like numerical simulations, and also Newtonian sintering, like a model for formulating the bonding between the extruded filaments. However, we noticed that, for example, using this approach by itself, which is just entirely physics-based, has limitations because it doesn't capture some physical phenomena. For example, there would be some filament or some bead deformation that caused by the creep or stress or for example the gravity. So how to incorporate that deformation to increase the prediction accuracies, that's what we try to address. And for that purpose, for example, we trained a neural network that could characterize that deformation, and then we just incorporated that deformation into this physical model to kind of enhance the prediction accuracy and also update the void boundaries. So for example, here you see some of our results where on the left charts or on the left graphs, the orange basically dots are basically the proposed method or what we proposed and what we could achieve. The blue are experimental data, and the black cross is basically what the state-of-the-art literature or existing models in the literature could achieve. So you can see that both with respect to the interlayer and intralayer necking radius prediction, we could actually outperform the existing models just by, for example, incorporating the data-driven models into the physics-based models in a hybrid form. So again, not truly integrated, but kind of combining them together and using them to their advantage. And on the right, you can see how we try testing our model on a spatial distribution of the void area. And you can see that the predictions and the experiment results kind of matched well. So this is, again, a typical example of how hybrid processes or hybrid physics-based and data-driven approaches look like. Now, we want to go one step beyond that. So we want to see how to truly integrate physical knowledge into machine learning and data-driven algorithms. And there are different ways that people generally use in the literature. So I would say that the most frequently observed approach that I've seen in the literature is loss function augmentation. And I will talk about that. But before I talk about loss function augmentation, I want you to look at the input feature engineering. So this mechanism is to kind of inform the model input or the data-driven input based on your physical formula or domain knowledge. So it's very, very similar to hybrid methods. So the output of one could be the input of the other, or like in sequence-wise decision making. So again, from my perspective, this category, I wouldn't call it truly physics informed. I mean, it's physics informed, but it's not truly integrated. So the truly integrated approaches are the two, and these are again the main ones. So there are different other approaches that are available, and these are the most important ones I've seen. So the most common one is loss function augmentation. So in this approach, the physical knowledge or the domain knowledge basically is infused within the loss function of your machine learning algorithm. So basically you have a loss function, and the loss function helps you to train your model and make the predictions of your model as close as the real observations. So if you have, for example, some physical constraints or physical knowledge that you can incorporate into the loss function, that's one way you can fuse this physical knowledge into the data-driven approach. So I will talk about this loss function in the next slide, but before I go through that, I want to say that in our group, we also proposed a different way of infusing physical knowledge into machine learning algorithms, what I call architecture shaping, which is on the right. So instead of trying to incorporate the physical knowledge into the loss function or some parameters of the neural network or the machine learning algorithm, we try to formulate or basically shape the architecture of that according to the physics or the process physics or the domain knowledge that we have. So before I talk about our approach, loss function augmentation, as I said, is the most common approach that has been used in the literature. And as I said, the loss function, as you can see here, So loss function is basically allows you to make sure that the model is feeding the data very well, and then you can get as close as the actual observations in terms of the results for the predictions. So the loss function augmentation methodology tells you that you can incorporate additional terms or add additional terms to the original loss function of your network. And this additional term that you're adding actually could be based on some experimental observation or some theoretical physical knowledge or constraints that you already have. So let me give you an example. So let's say you know that from like physical experiences that parameter X and the outcome of your observation, I don't know, like the tensile strength of the part and the input process parameter X. So let's say process parameter X and the output is tensile strength. So let's say you already know based on some experiments that these are positively correlated. So if one goes up, for example, in terms of a value, the other also theoretically should also go upward. So if you have that domain knowledge or that physical insight, it's very easy to incorporate it into the loss function. So if, for example, the X value goes up and then you have a model that after X goes up, it predicts as a Y that actually goes downward, so in the opposite direction, and you know from experiment that, okay, that shouldn't be happening. So what you can do is that you can easily incorporate like a penalty term into the loss function here. So this basically makes it physics informed. You know that based on physical observations that this shouldn't happen, so you penalize that behavior by your network so that your network eventually learns that that's a behavior that shouldn't happen, and then will adjust the weights accordingly. And there are again different ways you can do that. This is just one simple example of how this methodology works. And the traditional loss function augmentation methodology that we've seen in the literature, they're also commonly known as PINs. I'm sure you have heard of them, PINs. So they use loss function augmentation to make the neural network physics informed, and they're really good for solving partial differential equations. And now this is again a very methodology, but we came up with a different methodology for making our network physics informed, and that's by basically manipulating and shaping the architecture of the network. So the methodology we use, we call it architecture-driven physics informed deep learning. So what it does is that it relies on an iterative function or inference model. So why it's good for thermal history prediction? Because thermal history, we know that it's iterative in nature and it's like a time series. So for example, the temperature at time t+1 is a function of temperature at time t, of course, with some function, you know, so that function, you know, like it's generally like a nonlinear function that we theoretically know. And there are some parameters associated to that, for example, define the conduction, convection, and radiation, depending on the material properties and all that, right? So we know that the temperatures are related in a cyclic way. So if we know that iterative connection, then what we can do is that we can kind of unfold or map each of those time iterations to a layer of a deep network. So then each of those iterations in time would represent one layer, and then the weights of the layer which are used for training and fitting the model will be mapped also to the parameters of the model, the coefficients of the physical model. So now they will become interpretable. They have a meaning. The weights, when you optimize the network, the weights by themselves don't have a meaning, but if you map them to the coefficients of a model that, for example, talks about the coefficients, for example, for conductivity of this specific material, then you have you can actually interpret the model. And also the connections of the layers comes from the physical model in this approach. So you can see that you will end up with networks that are not fully connected. So the connection, if a connection does not exist based on a physical knowledge that I have, then I'm not going to add it in my network. And that actually saves a lot of time and computation cost. And the sparse network that has been created here also makes it very suitable for training when you have limited data available. So I'm going to skip the API ideal structure and moving to the case study. So of course, we wanted to check whether our methodology works. And we actually worked together with some of my collaborators with Argonne and also High State University. And we had like single track experiment, and we tested the predictions of our model with experimental data. And as you can see, they match pretty well. So there are some inconsistencies in these regions where the temperature goes above a specific limit. And we believe that in terms of physical phenomena, something's happening that our original physical model is not capturing that. So our hypothesis is that by incorporating those information into the physical model, we can actually capture these regions as well, the changes that are happening in this region. And we also compared the API ideal model with some existing models in the literature, all mostly data-driven. And you can see that on the right is our approach. And in terms of the error is much, much lower than the other methods. In terms of computation time, it's still much better than deep learning, which is fully connected networks. But of course, some other models still outperform it a little bit. But still, in terms of training time, it's still like within like a matter of like seconds or just 1 minute or something, which is still good for real-time monitoring and control. Now, the last question I want to talk about is basically the title of this talk talked about data efficient learning, right? So we wanted to see whether API ideal is truly data efficient. So because of the sparse network that it has. So we wanted to see how much of the training data would be enough for our API ideal model to get a reasonable level of accuracy in predictions. And what we did is we reduced the training data significantly and compared it, of course, with the two best methods from the previous slide. And the hypothesis was that as we move to the regions where the data becomes really scarce and very limited, the gap between the performance of our method and other methods should kind of increase, meaning that it shows that this physics-informed methodology works really, really good when data is limited and not available and not abundant. Yes, the experimental results and all approved this hypothesis. And we're so excited to actually continue exploring the application of this methodology. So to conclude, I basically, this talk mentioned that it's possible to merge physics-based models and deep learning models in many ways. So examples include feature engineering inputs, modifying the components, and modifying the architecture, which is what we do in our research group. And I honestly believe physics-based deep learning models will will play a significant role in AM-enabled mass customization scenarios for fast certification and qualification of the products, especially when we have limited data, and we will definitely observe a surge of interest and publications in the coming years. So with that, I just want to thank you all and all my collaborators and students. And thank you so much. I will be happy to answer any questions.
Thank you so much for presenting that. I have a physics background, so this was exciting for me to listen to. There are two questions in the question box. If you have questions, please drop them. The first one: which of the physics-informed approaches are better?
Okay, so this is a great question. So it's really hard to say which of them would be better because it really depends on how you define better. So of course, each have their own advantages and disadvantages. So for example, the architecture shaping methodology that we proposed requires the model or the physical model to be iterative in nature. So if you don't have a model that has that type of form, it's really hard to use our methodology. And it's also interesting to specify, as mentioned, is that it's not necessarily that these models are competing with each other, like one is better than the other. You can actually integrate both. So I could have a physics-informed neural network that both the architecture and loss function are modified based on the physics. So you can incorporate both of them together to make the model even smarter.
Great. Another question here: is this applicable to the FDM 3D printing process?
So yes, so anything, for example, for the FDM, same thing. You have also thermal history, right? So thermal history in nature, as I said, it's iterative in nature. It can be applied for both the FDM, the laser powder bed fusion, the direct energy deposition, everything that's thermally induced and has a thermal signature. Yes.
Great. What other AHEM application, in addition to thermal signature modeling, do you envision the API-DL approach being used for?
So this is, again, another great question. So as I said, the API-DL approach works really well when you have an inference model or a model that is iterative in nature, a physical model that's iterative in nature. And you can imagine that, for example, for topology optimization in additive manufacturing, you generally do the optimization in a state by state. So you do it in a sequence. So every state or iteration of your optimization basically enhances the design or the topology by a certain level, right? And then you build on that, and then again, you go on and go on until you get to the final optimal design or the topology. So it is, again, in iterative in nature, that process. So we can actually use the same approach, API-DL, and apply it for additive manufacturing design. Design for additive manufacturing. So anything, as I said, or any type of, for example, optimization problem that you have in additive manufacturing that generally is solved in an iterative way. For example, you use a gradient descent approach to solve the optimization problem. You can still unfold it using the API-DL methodology. I think you're muted, Adi.
Thank you.
Sure.
There's another question here from Esther. Would this kind of approach be utilized to use layer by layer in situ measurement data to protect the quality attributes of final product?
Yes, Esther, thank you so much for the question. So yes, it can be applied for that. So what we have done, so again, when you say layer by layer, you see the iterative thing comes to mind. And that's why this API-DL is very suitable for additive, because additive is a layer by layer process. So it has the trait that we need for API-DL. So right now, we only use the time basically, or the time periods, as the iterations. You can define the iterations as layer, so one layer from another layer to another layer. So it really depends how you define it, and either way you should still be able to use this methodology. Yes.
Perfect. I believe you've answered this one question, but I just want to share if there's anything else. This person is trying to confirm if this is better for polymers or metal, and if this model is dependent on method of printing.
So as I said, the API-DL methodology, so the loss function augmentation method that people are used is not really limited to any type of additive manufacturing process. It really depends on what type of physical knowledge you want to infuse and how you want to infuse it, like what type of constraints you want to add, etc. For the API-DL, so for example, if you're trying to do thermal signature prediction, so of course it applies to mainly, for example, to fused filament fabrication process, or laser powder bed fusion, or direct energy deposition. So anything where you have a laser source or some thermal energy that is like fusing or bonding the material together. It might not be useful for other types of processes, but specifically for this process that are mentioned, it would be most suitable. Yes.
All right. I think this is all the questions. This is everything that we have for you regarding questions. Thank you so much for your time. Thank you for presenting your work. If you're interested in what Professor Azadi does, please follow her on LinkedIn. And I believe she'll stick around during the networking session. Please find her there, ask her more questions, collaborate with her. I live in Chicago, so I promised to visit our lab so I can learn more about our work. And for some of you who are coming to Rapid this year, she's here in Chicago. Please feel free to stop by and see what she's doing and be a contributor to some of our work. Thank you so much for your time.